So let's look at part B. From part B, we know that we have this twist that 3 of the guardians are lazy, and what they do is they randomly ask one of their non-lazy friends which answer to give. So they behave 1/3 of the time like begone guardians, 1/3 of the time like honest guardians, and 1/3 of the time like malicious guardians. So the question in part C is asking, with that setup, but we get to ask questions of all 12 guardians, if Orpheus wants to extract only a single prophecy, how should he proceed? And what's his probability of being successful? So let's start with the first. How should he proceed? Well, if there's only one question that they want the answer to, it's pretty clear that what Orpheus should do is just ask everyone exactly the same question. What's the question? What is the date of prophecy 1 encoded as in the hint? So that's the question. It's pretty obvious that has to be the answer, because he has to ask one question to everybody, and this way he'll get all the same answers from the honest ones, and malicious ones will try to mess him up. So what is the probability of him being successful? The thing on this question is, it's not immediately obvious what's the situation. So you first ask, well, let's ask the easier question. What would be the probability of success if there were no lazy guardians at all? So if there are no lazy guardians, if no lazy, there's 3 honest and 3 malicious. In this case, what would happen? Orpheus gets 3 honest answers, but he also gets 3 malicious answers, which might as well agree with each other. So he has 2 dates that are coming back to him, both of which have 3 answers. So what can he do in that case? Well, all he can do in this case is he guesses. Between these 2. And so the probability of success is 1/2. If there were no lazy. Once you solve this basic case, you begin to see what you expect to happen in the problem as stated. Because no lazy, this is the same as all lazies say begone, which can happen. But now let's look at the other cases. What are the possibilities? Begone, begone, begone. Begone, begone, honest. Begone, begone, malicious. And then there's begone, honest, begone. Begone, honest, honest. And begone, honest, malicious. And then it keeps going like this. So the first thing you notice is, this we've already covered, but this case, what happens? In this case, you have one more honest guy than malicious. So this case, probability of success is 100%. He'll always get the right answer because he has 4 honest answers. Whereas over here, probability of success is 0 because the malicious guys outnumber him. And so you begin to see that there's a symmetry. That for every case where he has one more honest guy than malicious, he has another case that's possible where he has one more malicious than honest. Because just as you have these BHB, BHH, BHM, you similarly have BMB, BMH, and BMM. So they always bounce. So observe all cases with more H than M are balanced by cases with more M than H. So by symmetry, probability of success is 1/2. Why is this? Because we know that if there was no lazies, it's completely balanced. But the lazies are equally likely to be begons, honest, and malicious. Most importantly, they're equally likely to be honest and malicious. Because of this balance between honest and malicious, neither side is going to win. So the probability of success is going to be 50%, 1/2.